In the last video, we looked at how, given a second-order differential equation with constant coefficients, like this one, ay double prime plus by prime plus cy equals 0, how we could take a guess solution of e to the rx, because e to the rx has certain nice properties when differentiated. We get this quadratic auxiliary solution, characteristic equation, of the differential equation, whose solution r to this quadratic equation, when we plug these r's into y equals e to the rx, we get two distinct solutions to the differential equation. And this is when we have two distinct roots. And of the three cases of parabolas, we remember we either have two distinct real roots, one real root, or two distinct complex roots. Okay, now that we have these two solutions, let's think back and see if we can find a way to find the general solution. We're going to put it down here because we're going to get it soon. The general solution to our equation, differential equation, I should say. Alright, now what thinking back do we have to do? Well, not that far back, actually. If we remember, the differential equation operator, in many quotes, takes in a function. So it takes in a function, and it spits out a new function, something like a times the function you plugged in its second derivative, plus b times its first derivative, plus c times the function itself. This is the differential equation we're working with above. In a few videos ago, we showed that this operator is linear, which means that it satisfies two properties. If we plug in the sum of two functions, and I really should do probably general functions, so s of f plus g, we'll get s of f plus s of g, which is a very mathy way of saying the sum of two functions is, when we plug it into this operator, it's the exact same as just applying the operator on both functions. So if we plugged in two different functions to this differential equation, added them, we'll get the sum of what the differential equation on each function individually is. Second property is that if we take some scalar k times a function, this f isn't necessarily the same f as up there, so I guess I should change this to an h to be clear. Then we get k times the operator applied on h alone. So constants can be factored out. Now, given these two facts, we remember that we could make a general fact that it incorporates both of these, which is, I guess, what we should be remembering. So s of some constant times a first function plus some other constant times a second function. This is equal to the first constant times s of that function alone plus the second constant times f of that second function alone. This is the most general way of stating that this differential equation operator is linear. It has linearity. So now, this general solution, we know two facts. When we plug in to this s operator, when we plug in s of, I guess I'll do green. I am switching colors on us so many times. If we take s of y1, because y1 is a solution to the homogeneous equation, we get 0. And when we take s of y2, we also get 0, because y2 similarly is a solution to the homogeneous differential equation. So, with both of these facts, we can use the fact that s is linear. We can use s's linearity to say that you know what else will be a solution? S of some constant times y1 plus some other constant times y2. This will also be a solution, because if we expand it out, this is going to be k1 times s of y1 plus k2 times s of y2. And what is this going to be? S of y1 is 0, s of y2 is 0. This whole term these two terms, they're gonna add to 0. So our general solution, in some sense, we could say the general solution might look like this. It is y sub g, the general solution, is some constant, which I'll rename as c1, times y1, our first solution, plus c2 times y2. And I like the way it's phrased here because we don't even need this to be the solution to our homogeneous differential equation necessarily. If we had, although this is good for homogeneous differential equations, if we have any two solutions, then a general solution will be their linear combination, any scaled combination of your two solutions. And of course, for this to be true, you need y1 and y2 should be, again, linearly independent, because otherwise what you could do is you could say, well, if y1 and y2 are the same function in some sense, then we can factor them out, and we get y1 plus c1 plus some other constant c3 that represents how they're scaled. And obviously, this here, you just bunch this into a new constant. You get c4 times y1, and then this is no fun. So you do need y1 and y2 to be linearly independent. So y1, y2 must be linearly independent for this to work. But if that's true, this will happen. So let's just take a peek at what this might look like applied to an actual differential equation. So we'll just remember that our general solution is c1 times that first solution, e to the r1x, plus another constant times our second solution, e to the r2x. Okay, so let's pretend we have the differential equation y double prime plus y prime minus, alright, well, you know, let's make this slightly different so we get a nice root. So let's try plus 3y prime minus 4y. This is equal to 0. If we're looking for a general solution, our first step will be to find the characteristic equation of this differential equation. Now the characteristic equation, if you remember, is if we plug in the trial, or the guess solution, of y equals e to the rx, what we get is that y double prime is going to be 1 times r squared e to the rx plus 3r e to the rx, that first derivative, minus 4 e to the rx equals 0. And then we can factor out the e to the rx, and it'll never equal 0, so we get that the characteristic equation is r squared plus 3r minus 4 equals 0. And if that seems like witchcraft to you, maybe go watch the previous video because I explained it more thoroughly there. Now, given this characteristic equation, what are some different roots that we might have? Well, immediately we can see, hey, we can just factor this out. What we get is r plus 4 times r minus 1, that this is equal to 0. Okay, great. That means that the two solutions for us are that r equals 1 and that r equals negative 4. Okay, so now we know that in theory we have two linearly independent solutions. y1 equals e to the 1 times x, and y2 equals e to the 4 times x. Now, if we wanted to verify these are both solutions, we could plug them back into the differential equation, but I'll leave that as an exercise for you to do if you would like. Now, what we have is that we can come back and actually make our general solution. So if we come back up to here, we can formulate our general solution. We have the general solution is y sub g equal to some constant times our first solution, e to the 1 times x, just e to the x, plus some constant times our second solution, e to the 4 times x. And because of linearity, we can again break this apart each individual term, when we plug it into the differential equation, it'll equal 0. So these constants don't matter in affecting the actual solution, that it is a solution, but they will give us different solutions. And because e to the x and e to the 4x are almost trivially linearly independent, this is indeed a solution to our differential equation.